Hello and welcome to Hydrogeology, GEO420 at the University of Montana. This is Makeup Lecture 1. And we're going to continue talking about precipitation and get into evapotranspiration and talking about, um, you know, parts of the hydrologic cycle that we need in order to determine things like recharged groundwater aquifers. So when we left on Tuesday, we had talked about, or I'm sorry, I guess that was last Thursday, we had talked about the isohydral method of calculating the total volume of precipitation within a basin just using these point measurements. So recall that the idea was that um, we measure precipitation at a series of points within the watershed, and that we're trying to figure out how we interpolate or extrapolate those point measurements to the area of the full watershed. So I'm going to share my screen here, and we're going to talk about another method that can be used, another hand-drawn method of interpolating between these points. So recall that we had this basic sort of watershed that we talked about on Thursday, and in that watershed we had this series of points. All right, and the idea was, how do we take these point measurements and figure out how we calculate the precip across the whole basin? And this isohydral method was basically to break the basin up into polygons that are bisected or that lie directly in between each of the sampling points. All right, so the next method that we're going to talk about, sorry, that was not the isohydral, that was the Tyson polygon. Tyson polygon is this idea where we make these polygons that are bisected, and the distance is halved in between each of the stations. The next method we're going to talk about, is the isohydral method. So the isohydral method. And this is basically just a fancy way of saying contour precipitation. Okay, so I'm going to try and, as best I can, redraw my watershed that I drew up here. All right, and I'm going to try and remember sort of what I had drawn for precipitation measurements. So it's not going to be perfect, but we had a watershed that looked roughly like this, right? And here was the outlet. And we had points here, here, here. Scroll back up really quick. Here, here, and here. And this one was 6, 5. I think we had a 3. A 2.5, a 3, and a 2. All right, so here we're just going to contour, and contour rules apply. So some of those rules are that that contours cannot cross. A contour can't just end, so contours must only end at boundaries. And sort of a corollary to that is, or they're complete loops. All right. So they can't cross. They must either end at a boundary of the watershed or are a complete loop. And then a third requirement is that they a third requirement is that the contours, all points below the contour value have to be enclosed in that contour. All right, so if we follow these rules, there's no right way or wrong way to, well, there's definitely wrong ways if you break the rules, but there's no absolutely right way to contour. I'm gonna make a fourth rule: contours must have even intervals. Okay, so the first thing we do is sort of decide on the interval. And here I'm just going to do an interval of 1. All right, so each contour will have an interval between it of 1. And I'm going to make my contour intervals. I'll make my contours green. All right, so my first contour would be 1. And I don't have a measurement of 1, but I have a measurement of 2. And I'm going to just start off by drawing a contour here, has value 1. All right. Now I'm going to draw a contour value 2. All right. And if my point 2 has to lie on this contour. All right. So here's 2.
Now I'm going to draw a contour of 3. All right, what do I know? Well, I know that that I have 2 points 3 here that are going to lie on that contour. Now, all my contours here are ending at the boundaries. All right, and here 2.5 is less than 3, and it's enclosed by the 3 contour. All right. Okay, I've got no value for 4, but I do have a value for 5. And I've got a couple ways I could do this, but I'm going to do it this way to make an example. So here's a 4. All right. And now I'm going to do 5 like this. All right. Here's a 5. Now I've got a 6 here. I know I need another 5, so I'm going to bring another 5 here. And then I'm going to bring 6 here. All right, I've broken no rules. This is a valid way to contour this. And I could totally do it this way. You could also just draw a single contour that went over here. Both of these are valid. You have no data here to tell you different. And potentially you could argue that bringing these up to the edge here doesn't make a lot of sense. And so another way I could contour this would be to get rid of these 2 ends here and just make a single contour that went across. Something like that. All right. Either way, it works. It's legal. Okay, so now each area here, A1, A2, ... to A sub I. And now, this is A1, and it has a precipitation P1. And this P1 is the average precipitation between contours. Well, the contour less than 1 would be 0. All right. So the average precipitation between 0 and 1 is 0.5. So that is the average between contours. So here, this would be, for P1, it would be 0.5. For P2, it would be halfway in between 1 and 2, 1.5. All right, and it's terrible, 0.5. My notes software is really running slow at the moment. Okay, and this one would be A3 here. and P3, and here P3 would be 3.5, all right? And then in order to calculate the average precipitation, so my average precip would be, I'm going to use essentially the same formula as I did for the Tyson polygons. So this is the sum over my n contour intervals, or isohyets, and it would be P sub I, A sub I, all right? And I sum this over A sub I. We call this the area weighted average, and this is the isohyetal. All right, if I just wanted the total precip, I didn't want the area, well, then I would just sum P sub I times A sub I, and I wouldn't divide it by the area. But this is the area weighted average, and it will be in units of length. All right, if I wanted volume, then I would not divide by the area, the total area. Okay, so these are two ways to take our manually take our point measurements. So we always measure precip in points and interpolate them across a basin. All right. There isn't a right or wrong way to do it. People use both of these methods. What's important is if you do the contour method, you don't break the contour rules. If you do the if you do the Tyson polygon, you don't break those rules, all right? But basically there are ways of coming up with area weighted averages from these point measurements. Now, we have lots of ways of adding more data to have sort of a data informed interpolation method. And so the common way that people would, that in the future, if you were tasked with figuring out the total precip in the basin, well, if you have point measurements, you can of course do these methods, but you can also use these gridded data sets that are produced by several labs nationally. We're going to look at one right now that's called GridMet. So, so spatially interpolated data sets are data sets where they're using sort of computer programs to do this similar exercise, which is take these point measurements, figure out how to interpolate them across the landscape, but they might use things like elevation, aspect, distance from the ocean. They might use things like radar returns and even modeled precipitation, all to help determine how to interpolate between stations. So spatially interpolated data sets. And I'll give you guys two names so that if in the future you need to do this, you know some names of data sets to look at. So one is PRISM, and this is done by folks at Oregon State University. And then the other one is that we're going to look at right now is called GridMet. And this is done by folks at Idaho State. GridMet takes advantage of PRISM data and then adds in modeled precipitation. So PRISM uses only relationships between precipitation and landscape position to interpolate between points. And GridMet then adds in modeled precipitation from weather forecasting models. They both have their advantages and disadvantages, but we're going to look at GridMet right now and just look at what it produces. So if I was to ask you, you know, as a client to get me precipitation over a watershed, you have various options. You can do what we just did, a hand-drawn method, and that's viable. But you can also go and extract some of these spatially interpolated data sets for your watershed as well. So let's have a look here at GridMet. And in order to do that, I will stop sharing this screen and share this one. So here's GridMet, and it's a data set of daily precipitation, and they say high spatial resolution, so 4 kilometers. What that means is they'll give you the value of precipitation over a 4 kilometer by 4 kilometer square. All right, and it's called a pixel. So you can get it for each 4 kilometer by 4 kilometer square of the US. Let's see if we can just grab a let's see if I can just get an image. I'll download one and convert it to an image that we can display really cheaply. I'm gonna pause my recording here for a little while I do that, though, because you guys don't need to watch those mechanics. So okay, so here I've pulled up GridMet precipitation for the last 30 days. So this is cumulative precip for the last 30 days. And there's, I pulled up a map, all right? And so here's Missoula, here's Hamilton, here's the Bitterroot Valley, here's the southern Bitterroot Mountains, all right? Clark Fork, Flathead Valley, so the Mission and the Swan Mountains. And just want you to see that this is what GridMet produces. It's a gridded data set. And if I zoom in, I'm going to zoom in a little more, but you can see already these squares. Those are the pixels. They're 4 kilometers by 4 kilometer pixels. And we have a value for precip in that pixel. And you can see here that it's something like between 150 and 200, right? And you can see a couple things. Well, we have very little snow, if any, in the valley, and you can see there's been hardly any precipitation in the valley. You can see that in the mountains, however, there's been quite a bit, all right? And so you can see how variable the distribution is, and that the modeled distribution is consistent with observations that you get a lot more in the high terrain and less in the low terrain. And what's important is that these data are forced by point observations as well as topography and landscape position, as well as weather models. So a lot of, I'll say, thought went into how you interpolate between the point values here. And here's just sort of a national scale look at this. So, it feels like we're not getting much snow this winter, but we're in a much better spot than most people. So where I'm from down in southwestern Colorado, it's been a pretty horrible winter and very little precip over the last 30 days. Well, in the Northwest, we're doing pretty good. Lots and lots of rain here in the Emerald Sliver here, right on the west slope of the Cascades. And then again, for us here in the Northern Rockies, we're doing pretty good. And the Bitterroots appear to be doing as good as any mountain range in the nation at this point, other than the Cascades. All right, so this is sort of a more modern data set, and we can extract this data. There's lots of GIS methods to extract the data for just a given watershed. All right, so GridMet and Prism, two distributed data types. Okay, so that is enough on precip. You know, in many respects, probably the most or the best measured of the hydrologic variables, but again, we don't actually know exactly how much falls within a watershed. And so we have to figure out ways to go from these point measurements to the full spatial scale. All right, we're gonna shift gears now and start talking about evaporation and transpiration, and then we'll combine those two into evapotranspiration. So I want to start off with a drawing of the land surface. So here we are at the land surface. And again, I'll put a tree up here. My note-taking software is behaving significantly better at the moment, which makes my life much better. All right, and I'll put some shrubs. And of course, all these vegetation have roots. So I'll add some roots here. And we're going to add in a water body here, a lake. And a water table. And there's various places where we get evaporation. So we can get direct evaporation off of water bodies. So this is direct evaporation. We can get direct evaporation off of the soil. All right. And then plants use water, so we get transpiration through plants. And this is just the use of water by the plants. They pick it up in their roots and they move it out through their leaves, through their stomata. And we get evaporation from intercepted water, so water that falls on the canopy. So intercepted water. And so the total amount of evaporation and transpiration we lump. So we lump this into a term called ET, which is evapotranspiration. And that's basically all of these things that can lose water. So ET is equal to, and there's some other exotic ones, but for the most part, it's this intercepted water, directly evaporated water, directly evaporated soil water, and then transpired water. All right. So all this is sort of direct evaporation. And then this one is sort of evaporation is mediated by plants. So this is transpiration. So ET is, second only to precip as it's like the secondary flux of water in terms of magnitude in our watershed. So it's really a big flux. And most of it actually ends up being transpiration. Plants are really good at moving water from the soil into the atmosphere. And so they really pump a lot of water back into the atmosphere. So evapotranspiration is really hard to measure. So I want you just to think right now, like, how would you go about trying to measure evapotranspiration? Take 30 seconds and think about that. Okay, so the bottom line is there is essentially no way to measure it completely. And we have a couple methods that we use commonly. So the first method is called pan evaporation, and there we're measuring just how much water evaporates out of a pan. So we have these special pans. They're called an evaporation pan, and they're about 1 meter in diameter, and they're about, I don't know, 10 to 30 centimeters in depth. And we fill them in the morning, and we measure how much water left them during the day. And then that's not a direct measurement of evapotranspiration. It's just a measurement of direct evaporation out of this pan that has metal sides and metal bottoms. So we have to figure out how to turn that into some form of evaporation. So so how do we measure this thing? Well, we measure ET. There's a couple ways, and the first is an evaporation pan. And that's literally, it's a pan, flat pan of water that's like 1 meter in diameter, all right? And it's got, I'm pretty sure it's 10 centimeters of water. All this is sort of, formally defined if you're going to run an evaporation pan, but there's water in there, and we just measure the height difference over the course of a day. So that's the amount of water that left the pan is called EPAN. All right. And this thing's got sides, right? It's not infinite. And these sides heat up. So its evaporation is a bit higher than, say, evaporation out of a lake. And so we can turn this into an estimate of a direct evaporation through this constant we call Kpan. So you could estimate direct evaporation off of a water body using this constant Kpan. And there's a map of Kpan spatially across the US that you can go look up. But basically, this is how you take a pan evaporation measurement, turn it into a direct evaporation measurement. Now, this is still just direct evaporation. It's not ET. And so you can go to ET. I'm going to go PET that I'm going to define in a second. And that's just another Kpan ET times EPAN. And it's just another fudge factor. And it's just a different pan evaporation coefficient that has been tuned now to measurements of potential evapotranspiration. So let's talk about potential versus actual ET. So potential ET also gets called evaporative demand. And potential ET is the evapotranspiration, maximum evapotranspiration if moisture was not limited, all right? So in order to illustrate this idea, I want to throw this idea out here. So if I went out and measured the evapotranspiration in, let's say, the Sahara Desert in Northern Africa, the evapotranspiration, the actual evapotranspiration would be significantly less than the evapotranspiration, say, in northwestern Montana, let's say up near Glacier. And why is there that difference? Well, it's because there's no water in the ground in the Sahara, right? There's nothing to evaporate, whereas there's plenty of water to evaporate in the ground up near Glacier in western Montana. All right. So potential evapotranspiration is the demand. If there was water in the ground in the Sahara, it would go away at a high rate, but there just isn't any. So PET is the potential evapotranspiration. It often gets this symbol ET naught, all right? And this is the ET with no moisture limitation, no ground moisture limitation. All right, and that can be very different from the AET or the actual ET given the moisture limitation. All right, as you go on, you're going to have to learn to distinguish whether somebody is telling you PET or AET, and those two can be very, very different. Like I just said, the PET in the Sahara Desert would be extremely high, all right? But the AET is almost nothing because there is no water to lose, all right? So they can be extremely different, and our measurements here are of different things. So here in the pan, all right, you filled it up with water. There's no limitation here, all right? So you're measuring, you know, maximum transpirate or evaporative demand, all right? And so even when you're taking a fudge factor here and turning it into a PET, it's still a potential evapotranspiration. There's no way really to relate this to the amount of water in the soil. So you're always measuring PET with a pan. Another way we can measure, so this guy measures PET. Another way we could measure ET is via the radiation balance. And the idea is this. The idea is this, that you've got incoming solar radiation, all right, and that radiation, so I've got incoming solar radiation R. So if I make a little drawing here, you know, we're at the land surface and we've got sunlight coming in. All right, this is our main source of energy. All right, and when that energy hits the ground, it does a few things. It warms the ground, all right? So it heats the ground. And then it also is responsible for converting water into gas. So it heats ground. And then converts water into gas.